last situation to tackle. Then I'll speak a little bit about the upcoming test. And we're going to look at the difference then between two independent samples. So yesterday we looked at paired samples, right? Where it was a bit like a before and after, a male's age and the female's age, that kind of thing, where the data was really in like coordinates, pairs. And what we did then is we took the difference between them, called it D, and we created a 90, 95, 99% confidence interval. And that is how you should approach data if it is paired. If it's naturally got an A and a B together, an A and a B together, an A and a B, then you should do it that way. The other more common way, actually, this is more happens more often than not, is when the two samples are independent of each other. So you've collected one sample from some place and a totally different sample. It probably has more or less numbers in it as well. So let's do a pretend story. So in Scotland, they took a sample of 200 Scots people, and they found the average number of days in the week that they went out drinking, and it was 4.5, and the standard deviation for this data ended up being 1.2. And they compared it against the English, and in this sample there was 300, and the average number of days that the English went out drinking for adult males was 3.1, and the standard deviation was 0.8. Now you can see that there are different sample sizes, and Scotland was a whole load of people all Scottish, and England's obviously a whole load of people who are English, and these are independent of each other, right? Whatever the Scottish people do, the English don't have to do the same thing, right? They're totally unconnected. But we would like to know, is there a difference between Scotland and England? Do Scottish people, as it looks like, drink more often than English? So our quest here is to find a confidence interval that reflects the difference between the two groups. So sample one, here's the information. Sample two, here is its information. The first guy is, we need to know the degrees of freedom. Well, it's the smaller of these two. So you take this guy, subtract 1 and you get 199, and you take this guy and you subtract 1 and you get 299, and so you choose that as your degrees of freedom. Okay, it's not a biggie, but it could make a difference, right? It could be that is. So let's suppose that I'm interested in getting a 90% confidence interval for the difference. Well, I need to know what the magic T score for that is. So that's why I needed the degrees of freedom. I've got it in front of me here, so I'm not going to go back and forward. I'm just going to use it and zoom in it. And the number I'm going to come up with is 1.66, which is basically the closest number I could get was 100. So that's the guy I'm using. And it's time to put the package together. If you want to get a 90% confidence interval, it's x1 bar take away x2 bar, right? Plus or minus the magic t-score times the standard error of x1 bar take away x2 bar. Well, let's find out who x1 bar take away x2 bar is. it's 4.5, take away 3.1, so that's 1.4. There's a formula for calculating the standard error of the difference, and it's the ugly guy. It's this guy squared plus this guy squared. So I'll go over here and let's see what we get. I have the square root of 1.2 squared divided by 200, and I'm going to add to it 0.8 squared divided by 300. And the answer I got here is 0.097. Right, so I can put all that together now. The difference is 1.4, give or take the magic t-score, which is 1.66, multiplied by 0.097. And the answer I got was 1.66 times 0.097, which comes out as plus or minus 0.1, no, let's call it 16. And on one side it's 1.24, and the other side it's 1.56. So that's our 90% confidence interval for the difference between Scottish and English drinkers. This interval contains nothing but positive numbers. Great. From 1.24 all the way up to, it could be as much as 1.5 days. So I can make a pretty good conclusion here. I could say that it was statistically significant evidence that Scottish people drink more often than English people. I could even be a little bit more specific than that. Couldn't I say that on average they drink at least 1 day more? Right? It could be as much as 1.5 days, but not you could have a half day, but at least 1 day more. So we have got quite a good method of coming up with evidence. Analogy. Can you think of a court case where we're trying the crime that Scotland drinks more than English? Wouldn't this convict Scotland? This would be evidence that we could say is clear, positive evidence that the Scottish were less than English. So, to try a different story, let's suppose we took the age of Italians and people from Japan. And we found that the average age of Italians, right, all Italians, was 37.2, and that the average age of the Japanese sample was 41.7. And I took a sample of 30 Italians to come up with that answer. And I took a sample of 30 Japanese to get that answer. And the standard deviation on this group was 10 years. And the standard deviation on this group was 11 years, right? So in this case, what we want to know is there any difference between the average age of an Italian as opposed to the average age of someone from Japan? Would you agree that it looks like the Japanese are older than the Italians? Great. Now I'm going to use this question in a couple of ways. The first one is that we're going to take this data as is, and we are going to create a 99% confidence interval. So I'm going to see what kind of things I need to know. Well, I certainly need to know the degrees of freedom. Would you agree that the degrees of freedom is 29, since both are the same size? I need to know what the magic t-score is. Oh, by the way, in some textbooks, they actually put a little decimal next to the asterisk so that you know that this is a 99% one. This textbook just calls everybody, I think, T-star, but you will see in some texts they do that. Again, you can't see it, but I'm doing it for you. A 99% on 29 degrees of freedom is, if I could scan this, which is dangerous for me, is 2.76. I also need to know what the difference between them is. And I finally got a question where the answer is negative, because we were getting into the habit that everybody is positive. And a difference can and very often is negative. So there's the first guy, take away the second guy, and I got a negative 4.5. I also need to find what the standard error of this difference is. And that's this horrible formula. In this case, we are talking 10 squared over 30 plus 11 squared over 30. I should be able to do that on the calculator in one go. So 10 squared divided by 30 plus 11 squared divided by 30. And the answer I'm going to get here is about 2.71. So all I'm really doing right now is preparing to create a 99% confidence interval. Now, once I've got all the bits, we should be able to put them together and come up with our interval. So it's that guy, plus or minus that fella. Now the difference is negative 4.5, give or take 2.76 times 2.71. A lot of calculator work in this question. We come up with the answer, I'll round it off to 7.5. And what happened? Well, if you take that away, the answer ends up being negative 13, but if you add it, the answer ends up being 3. So what this is telling us is that the difference between the average Italian and the average Japanese person is somewhere between negative 13 and 3. The jargon that this textbook uses is it contains 0. You agree zero's in the middle somewhere. And then you have these little 4 or 5 sentences that typically follow. Wouldn't the sentence be this time that there isn't significant evidence that there is a difference? I'll rephrase that. There isn't significant evidence that there's a difference between Italian and Japanese average ages. And the reason for that is, on this side, wouldn't this represent the Japanese are older? And on this side, actually, the exact opposite is true, right? The Italians are older. What is the problem with this data? isn't that we collected it badly or we did anything bad. It's just that when we did the analysis, we weren't able to come to a conclusion. So we don't know. Based on this interval, we can't be sure. We look at this data set over here. Why do you think, what do you think the main cause of not getting evidence? Why do you think we never managed to get evidence out of this?
Sample size.
Sample size. If you want to get evidence, if evidence exists, see, I mean, if the answer is there isn't any difference, right? If the Japanese and the Italians are pretty much exactly the same average ages, right? Good arm, right? It doesn't matter how big your sample is, you shouldn't really be able to get evidence, right? You shouldn't be able to prove something that's not true, right? Even if you tried really hard, you shouldn't be able to do that. But if something is true, you need a decent sized sample to make that happen, right? You would expect that. Now, I'm going to make one change. I'm going to do a 90% confidence interval on the exact same data. There's only one number in this entire process that's going to change. And isn't that the magic t-score? Right. So if I go to a 90% confidence interval, I'm going to be using degrees of freedom of 29. And on a 90% confidence interval, I'm going to be able to change that number and it's going to become 1.7. So the 90% confidence interval is going to be the difference, 4.5, plus or minus 1.7. The standard error isn't changing. And now we have negative 4.5 plus or minus 1.7 times 2.71. Oh, shooting space. I thought I'd designed the numbers better, but nonetheless, I can do it. Doesn't that interval still contain 0? When I made up my numbers, I thought I could make it. So can you pretend just for a minute that this was actually 4.4, right? Just pretend it was 4.4. What I was hoping to do, if that was 4.4, is you get negative 9.9 to negative 0.1. Do you see that you might be able to get evidence at a 90% confidence level when you couldn't get evidence at a 99? How can that happen? Why has changing 99% to a 90% confidence interval changed your evidence from can't tell to there's now evidence that the Italians are younger than the Japanese?
I mean, you're allowing, it's not as confident, so you're allowing the possibility.
Right. And by reducing your confidence level, can't you change the interval? Essentially, what happens is that the interval becomes smaller. And when an interval becomes smaller, couldn't you then miss the 0 if you shrink enough? So you have to be careful when people tell you something is statistically significant, because something that's a 90% confidence interval is not as strong an evidence as when it's statistically significant at 99% level. Because in this world, couldn't I be wrong 10% of the time? If I say, yep, statistically significant, this is true, 10% of the time, I'm going to tell you something that's not true. Actually, it could be reality is the exact opposite of what I just said, right? 10% of the time it's wrong. If you do a 99% confidence interval, isn't there only a 1 in 100 times that you're going to make that mistake? So there is a balanced situation here between, I want to see if there's evidence to prove something, but I want to do it in such a way that I don't get it wrong too many times. So when they do confidence intervals, one of the decisions that the person who's analyzing the data has to make is a bit like the cost-benefit argument. Is the risk of being wrong and saying something's true when it isn't worth it for being able to prove certain things are true statistically? And I think you have to base that on what you're doing. And I've used this before. If I'm doing anything to do with medicine, people's lives, safety, go for the biggest and best to be safe, right? In fact, there's a 99.9% confidence interval. That's one of the ones that's not used as much, but it is used occasionally, that is used. And you know, for a 99.9% confidence interval, won't you feel comfortable about sending the guy to jail? Would you be comfortable, this is just an analogy, but would you be comfortable in sending someone to jail if you were only 90% sure that you'd got it right? I mean, wouldn't that mean 1 in 10 people in jail are actually innocent, probably, of the crime that you've committed them? So we would hope that our legal system tends to err on the side of being really confident. In fact, I would hope that they err on the 99.9%. So maybe only 1 in 1,000 people are in jail that shouldn't be. My wife likes watching a lot of crime stories, and there's a couple of things that come to mind now that, since I've said that, DNA has been a godsend for criminal cases, especially not just for convicting people, but you know, it's also been a godsend for saving people. A lot of crimes are committed, and the evidence, because of the way crimes are, is circumstantial evidence. But if there's enough circumstantial evidence, people get convicted, right? And there are very few crimes that are committed where there's 12 eyewitnesses and the guy before he died pointed at him and said, that guy's called John Smith, he just killed me, and then they keel over and die, right? That's not how murders get solved. Don't they tend to be solved because there wasn't a witness a lot of the time? And isn't it on shoe prints and left-handedness and all sorts of fibers and who knows, all sorts of stuff, right? So DNA, they went back and they looked at some cases, and the DNA that was found on the site couldn't be analysed like 30 years ago. But they've reanalyzed it, like cold cases, and they've reanalyzed it, and they've discovered that certain people were totally innocent, right? And so that's a good example. Now, there's only one way you can guarantee not to make sure that an innocent person goes to jail. And that is never convict anyone. But cost benefit in society won't allow that for very good reasons, right? If nobody ever convicted of any crime, what kind of world are we going to be living in? A very dangerous place, right? So we have to risk innocent people going to jail so that 99.9% of the guilty do end up in jail, right? And that's the balance. Certain countries have different balances. Right? I don't think I want to get convicted of a crime in, let's pick somewhere dangerous, in Russia. Because with my politics, I would be in jail. Guaranteed, they would not like me. Which is probably one of the reasons I'm never going to go to Russia, because they would probably convict me because I'd be protesting too much. I don't think they like protesting in Russia. No, they don't for some reason. Okay, so I feel comfortable about this guy, but I don't know, it's up to you. Do you feel comfortable on the two examples I've done to how to analyze 95% confidence intervals based on the data that you're given. Right. So I don't need to flog this dead donkey anymore, right? It's gone. Right. So what I want to do for the next little bit of time is look at some of the questions in the homework just to show you how they phrase them, right? Because they always do things their own little unique way. And then after that, I just want to spend a little bit of time on talking about your test. And just in case I forget, because I don't know who I tell and who I don't tell, what is special about tomorrow?
We don't have class.
So I did tell you, or you knew that anyway, David?
I knew that.
So that means I didn't tell you. Okay, everybody,
No.
I'm glad I remember. There is no class tomorrow. I'm doing an in-service training. So I will be here. Well, I'll be in Zoom, but I'll be getting trained. I don't know, maybe that surprises you that even at my age and the number of years I've been teaching, that we still have training, but it's different kind of training. They don't train me how to teach. Probably they should, but they don't. They would do things like, why do you spend so much time drifting? And my answer is, it's me. I'm a great believer, if you do teaching, I'm a great believer, just be you, even if it sometimes wastes time. It's just be natural. Okay, I don't know if you can see this yet, so I'm going to go out and in. If, come on, web thing, thingy. Right. Let's look at some of the homework questions. Here is question 1. It's a huge question and a very short answer. You might or might not know the first ladies for every single president, but here they are. Here is the age at death. So it's nice to know that they're not all dead, right? Would it be appropriate to use the ages of death of first ladies in this table and to find a 95% confidence interval for the mean? Well, what will we be using this table to collect data on? Consider the following data summarizing birth first ladies of the United States. I thought that question was easier until I read the details, and now I'm confusing myself. They're asking, is it appropriate to use the ages of death of first ladies? Well, it depends on what you're wanting to know. If the question is, I want to know the age that a first lady, the average age at what a first lady dies, then I guess I could use it. If I was using it to get the average age that all women in America die at, I wouldn't use it. So let's see what the choice is. Yes, it would be appropriate since there are more than 30. Well, that's true, there is more than 30. Yes, it would be appropriate since we can calculate mean and standard deviation. And the parameter is the average age of death of all first ladies who have died. Okay. This is a single sample. There we go, found the answer. Some of them haven't died yet. So until that happens, you haven't got a complete data set. So that's the one I'm going for. Nothing interesting here. Nothing that interesting here. Okay, these questions are basically number counting, crunching. You're going to find standard error. Right, can you remember when it's a single sample or when it is a difference or when it is two independent samples? Right, when it's this guy here, won't the answer be the square root of 17 over 100? Great. When it's a paired, won't it be the square root of 63 over 49? And when it's this guy, won't it be the one we just learnt today? The square root of that guy squared divided by this plus that guy squared divided by this. It would have been really better if they'd said N1 and N2 and S1 and S2 as different numbers. I think it would have been cleaner that way, but it still counts. Why does it still count? They are independent samples. So I would use that. Find the standard error, that's calculation. I prefer you didn't use so. Do you know I've got a table that I've got? The one that's on your spread on your Canvas site, use that one. Here, just find the number and write it down. Right, just find what the magic t-score is, right, for a 90% confidence interval. Use that table. Do you know the table I'm talking about? It's in Canvas. You click on it, it's got all those numbers in it, right? That's the table. It's got 29, 30, 40, 50, 60 down one side, and the columns tell you the scores. So you're going to use it to get those. Question?
Can you show us where the table is, please?
Yeah, let's do that. That probably was a better idea than me just pointing at midair, right? I'm just going to wait a few moments while I do all the things I need to do to get that, but it's going to make my life easier in the wrong. Right, move this over. There's our stats class. And here we are. So I will hopefully share that window and run basic on that one. Yeah, you should be looking at our Canvas site. You doing that? Right, you see the guy I'm talking about is this table here. It's called the t-distribution table. So when I click on it, it looks something like this. And if I do that one, and I make it as big as I can, suppose the question was the magic t-score for 13 degrees of freedom, a 95%er, right? 13 degrees of freedom, 99, you would use 3.01, okay? That's the number that you stick next to the standard error, right? So if you're doing a 90 or a 95 or a 99, you need this magic t-score, and it comes from this table, right? And if the degrees of freedom are not in the table, like 89 or something, right? If 89 is not in there, don't you just use the nearest guy to it? Very often, it's the same number anyway. So even if you actually picked the wrong one, you'd still probably get the same answer, so nobody would know. Between one particular value and the next, they don't change by much. So I wouldn't expect too much ever. That makes sense now? That's the guy I'm talking about.
Thank you.
So, right, so, oh, good question. Can I close this? Go away. Go away. Are you looking at question 7? Oh, good, I didn't need to go out and in. These ones I just think you should read. It's one of those that tell you something, you pick an answer, right? They tell you, I'm randomly picking answers here. And no doubt I'd probably argue out of some of these. Right. Some more standard errors. A standard error. 2 different questions. Standard error, standard error. Oh, I could talk about this one. Explain what happens to the magic t in each of these cases. See if you had a 90% and then you move to a 95. Would that t number get bigger or smaller? So you're 90% sure, but you want to be 99% sure or 95%. 90% sure doesn't have to get bigger, right? Bigger t makes the interval get bigger. So t increases. Suppose you kept the sample size the same, right? What happens if you look down the table? Well, when there's 100 or 200 or 2,000 on the same column, right? The same 90 or the 95, whatever it is, you will notice something very interesting about the t-value. It gets smaller. In fact, it finishes up being the same as the z-score. So you know the magic z-score for 95? The t-score for 95 is the same number when you get, I think it's 1,000 or 2,000. By the time you get to that size, there is no difference. So it decreases. And there's some more, same kind of story. Right. Don't use salt. Here is a classic. There's the mean. There's the standard deviation. There's the sample size. Do a 95% confidence. And when you're finished, I'm making this up, 70 to 75, right? That's all you write down. Or whatever it really is. Same question, lots and lots of practice, right? Oh, find magic t-scores again. That's all that is. Find some magic t-scores again. Oh, and find a 95% confidence interval for this story. And find a 95% confidence interval for this story. And then we are doing two groups now. Right, up to this point, I think most of the questions have been single sample and do what you need to do. Here we have two different groups. Volunteers who have developed a cold within the previous 24 hours were randomized to take either zinc or a placebo. So they're going to see whether zinc helps you recover from the cold, right? Quickly, compared to not getting any help. Okay, and it's a nice placebo, so nobody knows, I hope. 25 took the zinc, 23 took the placebo. The mean overall duration for the zinc group was 3.5, and the standard deviation overall for symptom was 1.2. On the placebo group, it took them 7.8 days, and the standard deviation is 2. Can you see in that question there, then you've got two groups and they're independent of each other, and you're just going to do very similar to what we did today, right? So this would be the Scots and the English, and all the numbers are in there. You just have to go hunting for them, and you're going to do a 95% for the zinc people, right? A 95% just for the other group. Actually, they're doing that separately. No, well, whatever. It's more of the same. Yeah, okay, we are good. So what's left? Whoa, God, time. We all know that your test is coming up on Monday, so you've got an extra day to do homework. I don't have it handy, so hopefully I can find it. Give me a second, I'll tell you. I shouldn't need to go through what to do in a test, because it's going to be exactly the same as we did in every other test, right? So, you know, don't phone a friend, all that good stuff. It's going to be a little bit different this time, because some of the questions have to be done on WebAssign, and some of the questions are going to be done on a PDF. So that is going to be a little bit clunky. I didn't want to do it all on the WebAssign, because that reduces your ability to show me the working. Because when you do a WebAssign, you plug it in and it gives you the answer, and that's fine, that's the answer, right? But when you have to do it through the working, it's a little bit different. So that's going to be the only difference. So what will happen is that when you turn up on Monday, there will be a PDF there with some questions, and they will typically be the ones that we've just finished doing, right? The proportion questions and the mean questions, right? So the difference between proportions and the difference between means. And then the other stuff, the earlier stuff, will be on WebAssign. So I think I've found the guy that I wanted to talk to you about. Right. Let's put it on here and show you what is what. So introduction to random samples, normal distribution, and I believe introducing. So the first three questions are going to be on WebAssign, and the last two questions are going to be on paper written down for you. So there'll be a story, you know, something like, who knows what I'll pick. The first one might be the percentage of women who like Pepsi is 40%, the percentage of men who like Pepsi is 30%. Find a 90% confidence interval. Is there any evidence that there's a difference between males and females in liking Pepsi? You know, that kind of question. And the other one's going to be a very similar kind of question. Average age of Italians, average age of Japanese, is there any evidence to prove there's a difference, right? Now, it might not be a double, it might be a single sample as well, right? It might not be a double proportion, it could be a single proportion. Those questions are going to be worth more points because you're going to have to do a lot of work in those questions. A lot of the earlier stuff is simply just going to go in and click yes or no to some question, or hit, you know, the one where you hit solve and you put in the number and it tells you the answer is 0.12. You remember those questions? Well, that's it. You can't get a lot of points for hitting solve and putting in two numbers, right? That's not really heavy duty working. So you're not going to get 20 points for each, right? So make sure you spend a lot of time doing the last two questions well, because that's where all the points are going to be. Any questions? You know the 5 topics. Some of it's WebAssign, but that's only because I want you to use SALT for those questions. And the others are going to be on paper. And so you only need to upload the working for 2 questions, the last 2. Right? The others won't need working because they're, you know, you help buttons in WebAssign. I've seen nods, so I think I'm good to go. And if there aren't any more questions, say hi and bye-bye. Do you have any questions? This is your chance. Okay, you're used to the tests, you know how they work and all that stuff, right?
Bye. See you on Monday.
Bye-bye, Cheyenne. Nakia, you got a question? You're hanging
No,
around?
sorry, I'm slow and then I'm distracted. See you Monday.
See you Monday.
Thank you.
Okay, Alexis and West, I'm leaving. Are you got any questions? Otherwise, I will close off.
I
Yes.
have a question.
Yes, West.
Wait, so what? I'm confused on the homework. That some of it's WebAssign and then what?
No. Homework's all WebAssign as normal.
Okay, then what's off of WebAssign?
Well, when you come to do your test on Monday, some questions will be in a WebAssign assignment and some of the questions will be in a PDF. So they'll be in 2 different places. The questions that are on WebAssign, you just type in your answers and call it good. And the questions that are on PDF, you show me the working. So it's a little bit of A and a little bit of B. So questions 1, 2, and 3 will be on WebAssign. They will be from your chapters. I've lost it down. They're from chapters 8 and 9, the intro to 9. And then the last 2, sampling and proportions and sample distribution, the last 2 questions, they will be on a PDF that you do working for.
Okay. So do we not have class tomorrow?
Correct. There is no class tomorrow.
Okay. Could we set up a Zoom so I could ask extra questions?
Probably not, because although there's no class tomorrow, I'll be at a conference tomorrow So I'll
Okay.
be pretty much doing that stuff. So I'm not sure I'll be able to be free. It's a kind of whole day thing, so I'll be doing it for the whole day.
Are you free Saturday?
I probably will be. I don't think I've got anything that I know booked on Saturday. Shoot me a time in an email and when you're free, and then I'll check with my wife in case we've got things, because
Okay.
we do stuff in the weekend like everyone else.
Okay.
Okay.
All right. Thank you.
Alexis, are you here for a question, or you just forgot to check out? I'll assume you forgot to check out. So